Hello class, welcome to the lecture video for week 12, day 2. Today we'll be doing firm optimal decision making, particularly cost minimization, and I'll look at output maximization a little bit. But we're going to focus mostly on cost minimization. So really quick motivation, hopefully you've done the reading, page 220 to 225. This cost minimization is basically a baseline model of productivity for economics. It's going to be the workhorse. So anytime you're asking a production question, regardless of whether it's like some traditional manufacturing industry or not, we're going to start kind of right here in the baseline. And so this is used in education, labor, health, macroeconomics, and industrial organization questions. So really wide array of applications for this. And there's 3 ways for a firm to minimize their costs. So when they're minimizing their costs, they're combining information about what it costs them to produce something, which is summarized in the Isocost curve, and efficient production combinations of inputs, which is summarized by the isoquants. And so they produce a given level of output at the lowest cost, which just basically means they have some target output that they need to produce, and they try to produce it at the lowest cost. And so these 3 rules that we'll be looking at today are the lowest Isocost rule, which is kind of the most informal way of doing it. They pick a bundle of inputs so that they get to the lowest Isocost curve, which is pretty intuitive. And then while we're walking through that, we'll see that the lowest Isocost is always where the Isocost is tangent to the isoquant curve. And so that's the tangency rule. And there's kind of a couple ways to interpret it. So we know that the slope of the isoquant is the marginal rate of technical substitution. So this negative marginal product of labor over marginal product of capital. And we know the slope of the isocost is just the ratio of the prices of the input factors. So wages over the cost of capital. So the cost of labor over the cost of capital. It's negative, obviously, because the isocost curve slopes downwards. And then finally, if we do some algebraic manipulation for the tangency rule, we can get to the last dollar rule, which is basically just says cost is minimized if the input's chosen so that the last dollar spent on labor has as much extra output as the last dollar spent on capital. So I'm going to walk through these and then do a quick example, and then we're done. So the lowest isocost rule is just the firm picks a bundle of inputs, so the lowest isocost line touches the isoquant. So here we have 3 representative isocosts and isoquants. And so we know the lowest cost of producing Q bar amount of output is C bar. So if you want to produce on this isoquant, the cheapest way to do so is using this bundle of inputs. And then the lowest cost producing Q bar prime. So this amount of output is to produce at C bar prime, or to use this combination of inputs, which just touches the C bar prime. And then same thing for the last one. And so let's just say for a moment the firm wants to produce Q bar amount of output. So this Q bar prime is just a number. I have Q because I don't want to have to choose a number right now. And we know points A and B are possible ways to produce Q bar. So if you have this combination of capital, like a lot of capital and a little labor at point A, you can produce Q bar prime amount of units. And because they're on this isoquant, this is literally what this means. Or if you have like a lot of labor and a little bit of capital at point B, this is another way that you could produce Q bar units. But something that's happening with this isoquant crossing this isocost is it crosses twice. And that means that there's a cheaper bundle of inputs that you can use to produce the same amount of output. And so you're basically throwing away money by using these alternative production bundles. And so the cheapest way to produce Q bar prime is to use this O prime combination of labor and capital that sits just on this C bar prime isocost curve. And there's no cheaper way to produce Q bar prime units than O prime. And we can kind of just see an appealing kind of fact about that is that it's tangent. So it just touches this isoquant Q just touches this isocost C one time. And that's the tangency rule. So their slopes are equal only one time, and that's at O prime. And so we can see here, mathematically, this point, like I've told you, is this marginal rate of technical substitution, which is how much additional, how our output changes as we change inputs slightly, equals the ratio of the prices. And so these ones here are the tangency rule, and then this last dollar rule comes from just manipulating this algebraically to get the marginal product of labor divided by wage needs to equal the marginal product of capital divided by the cost of capital, which is R. And so this left side is kind of not straightforward to interpret, but this right side has a really convenient intuition. That is, the last dollar spent on labor gets you as many units as the last dollar spent on capital. And so you could, like we kind of talked about earlier, make Q bar prime at either points A or B, but it's crossing twice. And so you could make the same amount and spend less. You could be on a isocost curve closer to the origin, meaning you spend less, which is good for business and profit maximization. And so if you can do that, then you would not want to be at points A or B. And if you only spent C bar, it's not possible to produce Q bar prime because no bundle of inputs on this isocost line is able to produce Q bar prime. You just don't have enough inputs there, or the right combination of them. And so I wanted to do an example for you, and I spent way too much time on this yesterday. So hopefully I can help you, and if you have questions, please feel free to reach out. So our question is, we just want to find the optimal mix of capital and labor. We're given this production function of Q equals 1.52, labor to the 0.6, K to the 0.4, and because 0.6 and 0.4 add to 1, this is the Cobb-Douglas production function. This is the only production function I'm going to give you in tests or homework. And we see A equals 1.52. And so we have a production function, and we have the price of inputs. Labor costs $24, capital costs $8. And we know that the manufacturer is looking to produce 100 units of output. And so how do we find the optimal bundle? The first thing we need to know is the optimal condition, which is the marginal rate of technical substitution equals the ratio of prices. And this is where the isoquant will be tangent to the isocost, the lowest isocost possible, which is pretty cool. We can just find that point with these powerful mathematical methods, which I think are cool. And so we're trying to find from these input, or not inputs, it's a bad word, these parts of the question, what is the optimal bundle? And so we need to find this. So the first thing, we have W and we have R. W is 24, R is 8, but we don't have the marginal product of labor or capital, and so we'll need to take a derivative of the production function with respect to labor and with respect to capital. So dq dl and dq dk. And so dq/dl, the marginal product of labor, is here. You can see I just multiplied 0.6 times this, and then subtracted 1 from the exponent, and I get this. And I did a similar thing down here, and so that's not too new. This part was really hard, or not hard, but took me a long time to figure out what they were doing in the book. And so you can There's a proof in the book that shows this, but the marginal product of labor will just be 0.6 Q over L. And it's weird that you can go from kind of this dQdL to this dQdL. What they're doing is substituting for Q. They're substituting Q back in for 1.52 LK. And how they do that is they're multiplying. So this will be L to the negative 0.4 on the bottom. And what they're just going to do is multiply both the numerator and the denominator by L to the 0.6. And so then you have Q on the top and just L on the bottom. And the same thing with K. That was really frustrating. And then once you have these, you can just plug these into one and solve. And we know that this Q here, the firm is aiming to produce 100. So we just plug in 100 for Q and solve. And after solving, we get the optimal K star is 2L. So we'll have twice as much capital as labor. And then we just plug K back into the productions function, back into this Q that we're given, and solve for L. And this one was also frustrating here, but it got a lot easier when I remembered that 2L to the 0.4 is the same as 2 to the 0.4 times L to the 0.4. And then from there, it becomes pretty trivial algebra. And you get L star equals 50 and K star equals 100, notwithstanding some rounding differences. And so that's the answer. We have our optimal bundle of labor and capital just from a production function and cost and a target output. Pretty cool. And we can go through and calculate the cost of using 50 units of labor and 100 units of capital by just plugging it in to cost equals wages times amount of labor plus cost of capital times the amount of capital. And we get the lowest Isocost curve obtainable is spending $2,000 to make 100 units in this particular example with these cost and production function. And so here's a picture of what that would look like. And as you can see, it's tangent right here to our Isocost curve. And kind of what we've done is gone through and minimize costs. Sometimes an alternative way to solve the problem, which I won't test you on, is using a Lagrangian to maximize output for a given cost, which is kind of the same thing, or you'll get the same answer. It's just kind of switching around what your objective and constraints are. And you would go through and solve this Lagrangian. And so I'm just going to be nice and not make you do that. So that's it. In conclusion, this is kind of like the last time we'll have to solve for an optimal bundle of something. So that's good for people who don't like this. And this is useful in a lot of different contexts, like I kind of alluded to earlier. And I showed you these 3 ways to find the optimal bundle of production inputs. And they're really pretty much all the same. And so I've released the homework, and you can get some practice on this in the homework. And I'll catch you for the next video.